The spin echo. To understand the spin echo, we have to revisit pretty much everything we've covered up until this point. But before we do that, I'd like to start with a question. Go ahead and pause here, and I'll go over the answer after I cover the spin echo. Okay, so where does MRI signal come from? It comes from hydrogen nuclei, which in the human body is mainly found in water and fat. We can think of hydrogen nuclei as functioning like tiny bar magnets, and we can represent these bar magnets as vectors with a magnitude and a direction. Furthermore, we can decompose these vectors into longitudinal and transverse components. Now we're going to start thinking about hydrogen nuclei as electromagnetic spins. So to gain more of an intuition for that, let's consider mechanical spins, spinning tops, like this dreidel. So I'm going to ask you a question. What would happen if you put a dreidel, or a spinning top, on a table and you didn't spin it? Well, the answer is that gravity would just knock it over, right? But what happens when you spin the top? When you spin the top along its long axis, you create an angular momentum, which is going to cause it to precess, or rotate around, the force that's acting on it, which is gravity. So something similar is going to happen with hydrogen nuclei, right, that are acted on by the force of B naught. That's the 1.5 Tesla magnet, or 3 Tesla, depending on the strength of your magnet, that's always on, right? So hydrogen nuclei have an odd number of protons in the nucleus, and that gives it this property of quantum mechanical spin. It's not unique to hydrogen nuclei. Any nucleus that has an odd number of protons will have this property, but we're focusing on hydrogen nuclei because they're just so abundant in the human body. So because this hydrogen nucleus has this intrinsic spin associated with it, when it's acted on by a force, B0, B naught, it's going to precess around it. So how does this new understanding of the hydrogen nucleus as an electromagnetic spin change how we think about the net magnetization vector? This is before we apply the 90-degree radiofrequency pulse. So the answer is it doesn't really, right? The net magnetization vector points in the same direction as B0, and it does not precess, okay? But the individual hydrogen nuclei, which sum to form it, do. So I'd like to talk a little bit more about that. So remember, how do we form the net magnetization vector? So for every 10,000 hydrogen nuclei, 5,003 are going to line up parallel to B0, and 4,997 are going to line up anti-parallel, such that for every 10,000 hydrogen nuclei, you're going to have 6 that point parallel to B0. And this is what's going to form the net magnetization vector. So now we need to think about the fact that these individual hydrogen nuclei are precessing around the axis of B naught, right? Because these hydrogen nuclei have this property of quantum mechanical spin associated with it, which causes them to precess. So what's going on? Why doesn't that lead to the net magnetization vector precessing? Well, the answer is that the transverse components of these individual hydrogen spins is going to cancel. So let's just consider these purple spins. So this purple spin, let's say it's at 12 o'clock on the circle of precession. I like to think of it as like a clock face. And then this bottom purple spin, let's say it's at 6 o'clock. So if we're going to diagram out the longitudinal transverse components of each of these purple spins, the transverse components, because they're oriented 180 degrees to each other, they're going to cancel. The longitudinal components, they're parallel to each other, so they're going to add up to something, right? They're going to add up, contribute to the net magnetization vector. So that's the same thing is going to be true for the blue spins, right? Which is at, one's at 11, one's at 5, 180 degrees apart. The transverse components are going to cancel. This one is at 9 o'clock, this one's at 3 o'clock. So again, 180 degrees apart, transverse components are going to cancel. So even though these individual spins are precessing, they're precessing out of phase with each other, right? At 180 degrees to each other on this clock face, on this circle of precession. And that's why they essentially cancel each other out in the transverse plane. So before excitation, spins are oriented 180 degrees to each other, out of phase, along the circle of precession. This lack of phase coherence results in no transverse magnetization, no precession of the net magnetization vector. Okay, so what determines the frequency of precession, F, of a nucleus around an applied magnetic field? So this is the equation, and I'm going to go through it. But the most important point to remember is that this frequency is mostly determined by the applied magnetic field strength. So if you're in a 1.5 Tesla magnet, the hydrogen nuclei are going to precess slower than if they're in a 3 Tesla magnet, right? That's going to be the dominant determinant of the frequency of precession, is the strength of the applied magnetic field. But it's also the result of this constant called the gyromagnetic ratio, which is going to be specific to each nucleus. So for hydrogen, it happens to be 42.58 megahertz per Tesla. And then it's also going to be modified by local tissue magnetic susceptibility. So we'll talk about this more later, but just as a quick example, if you have blood products, they demonstrate a property called paramagnetism. And it relates to the unpaired electrons that they have. And this essentially augments the local magnetic field strength to make it a little bit stronger. And so that's going to cause the frequency of precession to be slightly faster. So again, what determines the frequency of precession? It's mostly determined by the strength of the applied magnetic field, but it's modified by local factors as well. And I think that's a good start. What is the frequency of precession, F, of a hydrogen nucleus around the 1.5 Tesla magnet in an MRI machine? So this is the equation. Let's just plug in some numbers. We're going to avoid the local factors for now. So 42.58 megahertz per Tesla is the gyromagnetic ratio for hydrogen. Multiply that by 1.5 Tesla, and we get 64 megahertz. So this frequency, 64 megahertz, at least for a 1.5 Tesla MRI machine, this is sometimes called the Lorimor frequency. This is important, and let's try to see why. So consider what would happen if you caused a 64 hertz tuning fork to vibrate. This would cause any nearby 64 hertz tuning forks to also vibrate. So these tuning forks, they're not touching each other, they're just close to each other. But if you cause one to vibrate, the other one will start vibrating. Whereas the nearby 128 hertz and 32 hertz tuning forks would remain unaffected. So this illustrates the principle of resonance, which is essentially an efficient way of transferring energy when you deliver it at the natural frequency of the system that you're trying to deliver it to. So how does this relate to MRI physics? So hydrogen nuclei precess at around 64 megahertz, that's million times a second, around a 1.5 Tesla magnet in an MRI machine. So that's the Lorimor frequency. So based on the principle of resonance, what frequency do you think the radio frequency coil should be tuned to in order to rotate the net magnetization vector into the transverse plane? Remember, we need to do this in order to measure M, right? We need to separate it from B naught, because otherwise B naught's going to overwhelm it. So the question is, how do we want to tune the frequency of the radio frequency coil in order to do this, given this principle of resonance? So the answer is, you want to tune it to the Lorimor frequency, right? Which is going to be 64 megahertz in a 1.5 Tesla system. It would be 128 megahertz if you were in a 3 Tesla system, for example. So the rotating magnetic field generated by the radio frequency coil, B1, is tuned to resonate with the natural frequency of hydrogen nuclei inside the human body. Pretty cool, right? And it's called radio frequency, right? Because radio frequencies tend to be in that megahertz range. Not a coincidence. So how does the resonance rotate the net magnetization vector into the transverse plane? So the answer is phase coherence, okay? So resonance brings spins closer to each other in phase along the circle of precession. So let's explore this a little further. This is a very important concept, phase coherence. So this is how I taught excitation in part 1 of the course. So we're going to revisit it now that we're thinking about hydrogen nuclei as electromagnetic spinning tops. So now what's happening is that the net magnetization vector, it's not just pointing up, right, into the transverse plane after the 90-degree radio frequency pulse. It's actually going to be precessing as well. At what frequency? The Lorimor frequency, 64 megahertz, right? 64 million times a second. So that's what I'm trying to sort of illustrate with this rotating satellite picture. It's just, you just imagine that this thing is rotating. I didn't know how to animate that. Okay, so after excitation, spins are close to each other, i.e. in phase, along the circle of precession. So if you take a look at these yellow spins, for example, I would argue they're close to 11 o'clock on the clock face. And you'll notice that whereas before, they were 180 degrees apart, they were like 6 hours apart, now they're at the same time, right? They're in phase with each other. So the transverse components are not going to cancel. They're going to actually add up to something. That's what phase coherence is. You're basically at the same location on the clock face. So this phase coherence of the individual hydrogen spins is going to result in transverse magnetization, right? Doesn't cancel each other out. And precession of the net magnetization vector, right? So because the individual hydrogen nuclei are precessing, so is the net magnetization vector, because that transverse component is no longer canceling out. All right. So why are we able to detect the net magnetization vector in the transverse plane? So phase coherence, right? This is what we're talking about. But there's one other point I want to bring across. So when M is pointing into the transverse plane, that's actually not enough to be able to induce electricity in the receiver coil. Because based on Faraday's law, the magnetism has to be changing in order to induce the electricity. So this is a detail that I glossed over in the first part. So now we're ready to understand that. So because M isn't just pointing perpendicularly into the transverse plane, it's actually precessing at 64 million times a second, right? That means that effectively the net magnetization vector, the magnitude of it is going to be changing, right? It's going to be positive when it's pointing up. It's going to be 0 when it's at that point of the rotation, and then negative when it's at that point of the rotation. So it's going to be constantly changing. And as a result, it's going to be able to induce electricity in the receiver coil. That's how Faraday's law works. All right, so why does the net magnetization vector precess when it's pointing in the transverse plane? It's due to phase coherence. I'm repeating this over and over and over again. It's important. So because the transverse components of the individual vectors are changing as they precess around B0, and they're in phase with each other, they're not going to cancel out. So basically, it's not just the individual hydrogen nuclei which are precessing, it's the net magnetization vector is also precessing. And that's what allows us to detect it. Okay, so how do we go from this 90-degree radio frequency pulse state of the net magnetization vector, where it's precessing at 64 million times a second, to where we started, right? With the longitudinal magnetization, the net magnetization vector just pointing in the longitudinal plane, but not precessing. So again, we're going to refer back to this graph where we essentially lose transverse magnetization much more quickly than we recover longitudinal magnetization. So this is still true. Another way of saying this is that T2 is much shorter than T1. So what's going to happen is that we're just going to think about this happening while the net magnetization vector is precessing, right? So this is an animation to try to illustrate that. To me, I just think of it as like a Hershey's kiss, basically. So that's sort of the updated version of this graph of showing how you lose transverse magnetization more quickly than you recover longitudinal magnetization. This is the relaxation summary graph. So the updated version of this, now that we're thinking about hydrogen nuclei as spinning tops, it's just a Hershey's kiss.